Hi, everyone. Thank you very much for coming to this session today at Data-Centric Summit AI. I'm super excited. My name is David. I'm the founder of Activeloop, and we have very exciting updates today for the whole deep learning ecosystem and MLOps for data-centric computations. And today I'm going to talk and introduce a new category called deep lakes, which are optimizing data lakes for deep learning application. And I'll get into details what this is for. But before that, let's take a step back and see what happened during the last 3 years. We have seen that these foundational and large language models have been growing in their size. You now have trillion parameter size models that are trained across all the data that you can find on the internet, mostly textual, but now you're seeing also the images come into the place. And the trend that we foresee going to the future is that you're going to connect images, audio, videos, and text data all together into these large foundational models that will do a lot of useful stuff. And one of the first things that we have seen that making like magic because of this large deep learning models is the image generation from the text. You likely have seen across the Twitter going through Mid Journeys or DALL-E 2 image outputs or Stable Diffusion, where you can provide a very simple language text to the model and then expect generated photorealistic or sometimes artsy images that you can use for creative work. And this has went viral across the whole internet. And we are seeing including Stable Diffusion being open source and other models, and then looking into how these models have been trained on and how much impact they can have building more useful features down the road. And at every model that you see in deep learning and over the past 10 years, there is a data set that sits behind the scenes that has been able to create these models. And apparently, 1/3 ML projects, they fail because of poor data development practices, because of having the problem building those data sets and then fitting into machine learning frameworks. And apparently you have all these awesome databases, data warehouses, data lakes, now also called lake houses, specialized for analytical workloads to store the data and then feed it into like running queries or visualizing the distributions of the data, but they're not good use for complex data processing where deep learning shines. And furthermore, there's this notion of data lakes that came over the past 20 years for being able to centralize all your data into a single location and then easily integrate with the rest of the stack, which today is called modern data stack, to be able to do like run queries, visualize the data, and being able to orchestrate the whole decision-making process in your organizations. They have very great benefits, including breaking data down data silos, enabling data-driven decision-making, obviously improve operational efficiency of the whole organization because now all your team has access to the same data and they can make quick decisions. And then, of course, compared to storing the data across a data mesh, having them in centralized, cost-efficient storage that significantly reduce the costs. And now you see also a combination of a second-generation data lakes. They not only provide the following benefits, but also give you ability to be able to do time traveling across your data, ingest the data with parallel uploads, being able to connect with your favorite query engines, and then run the operations there. And then the further recent trend is so-called lake house that connects a data lake, adds with a query engine. Now it can actually compete against data warehouses and databases that are used for analytical, historical, and also predictive queries. However, for you to be able to use this all great technology for complex data processing, there are a lot of limitations. First of all, images, video, audio, they're not natively supported. And typically what you see, let's say in Lion dataset case, a Parquet file with additional column that points to the files on another storage system that you have to fetch the data to be able to train your models. Secondly, there's no native deep learning integration at all. So you can't just plug it into PyTorch or TensorFlow. You have to write this huge code to be able to go from the raw data, the way they store data sets in modern data stack to the deep learning frameworks. Furthermore, not only the modern data stack, but also there's MLOps ecosystem that's parallelly being evolved. And you have seen today many representatives of these technologies shown at the Data-Centric Summit and how they improve for your data development practices. And one as well major point that so far queries like SQL query engine itself has been focused on the use cases where, hey, what is my last month of sales activity that my company did? Or what are the future forecasts, how I can manage my inventory? But they have never been optimized for dataset building. That's very important for coming up with good deep learning models. And I'm super excited today because this is the first time that at Activeloop we are providing this publicly, releasing the category, the tool, the product, for you to be able to access and start using it, which is the Deep Lake, which is a simply vanilla data lake, just specialized for deep learning applications. With one difference is that it can actually support images, video, audio, connect to the deep learning frameworks, easily integrate into MLOps systems like annotation tools, experiment tracking tools, your training systems, and so on, and being able to visualize and query the data sets so that you can actually build good data sets for your training purposes. And I'll get into details what this good means in a bit. But that's what a deep lake is. It's a data lake for deep learning applications. Let me tell you where it sits in the whole MLOps ecosystem. We have been working with AI Alliance infrastructure together on coming up with this ecosystem map, which is the new blueprint for MLOps. And you can see it has three main components. The first one is the human foundation. The second one is the model foundation. And third one is data foundation. And you can see how it goes from bottom up to top, going from the infrastructure level to the user interface. And from the left is like the ingestion of the data to the production use cases. And you can see on the data foundation part where you have a need for data lake and data warehouse. We introduce here Deep Lake, which takes all the responsibility for maintaining structured and unstructured data sets, having a data lineage, and then very efficiently running queries and streaming it to the rest of the tools so that you can be able to do the processing in a very efficient manner for deep learning and unstructured data processing. The main problem is that today, data scientists manage their data as if we had developers had no any database technology at all. And we are super excited to bring this to the deep learning community to be able to leverage all the database technologies there, all the benefits that comes from it for your use cases. And that's where Deep Lake is coming into the place. So let me go through the workflow, how the ML lifecycle will look like when you deploy Deep Lake. First of all, Deep Lake gets in your raw data, including maybe already annotated data sets, puts into version control, lets you basically visualize the data and inspect the data set, maybe remove few examples, maybe edit the data set again, or send back to the annotation tool to be able to visualize that better, and then run queries. So you can take, let's say, a subset of the data set. You want only images in front of a bicycle with a car that you want to fine-tune your model. Run the query. This will return you a view. The view will be able to be, you can directly train the model on the view, but it won't be as efficient as if you materialize the view itself and then very efficiently stream the data from a remote storage to the training process as if the data was local to the machine. And then you have the rest of the MLOps tools taking care of the training process, evaluation, deployment, inference, monitoring. And then again, you repeat this loop again. One of the key things in any ML lifecycle is being able to close the gap and then continue these iterations as many times as possible so that you can get your models to be production ready, highly accurate, in some cases superhuman accuracy, basically that achieves better accuracy than as if the human will do those making decisions, for example, in self-driving cars, use case, and so on. So let's go through each step and see how Deep Lake helps you to do this. First of all is the version control. You can think of it as a Git for data, but there's no any Git running behind the scenes. It helps you to connect to the data, and then you can see the full lineage, how we can go from an empty data set, create an image tensor, which is your column, append 100 image links, which are the pointers to the references of your original data, create another branch, check out to that, add the annotations from the annotators of all those images, merge back the data to the annotation tool, to the main branch, and then be able to run a query, create the view, materialize the data set, and then stream it to the PyTorch training process. And when you train the model, you can backtrack and say, hey, this model has been trained on this data set. How this data set has been created, what are the links have been used, what are the data sets that have been accessed while I was doing the training process with a full, complete visibility. This goes in contrast with traditional data lakes where you only have a single branch history, which they call as a time travel feature. You can actually here be able to grow your data set with multiple branches, merge them back, and then be able to run the training process. Second thing is being the ability to be able to visualize this data at every step of your version. So what we enable you to do is that we very efficiently stream the data from your S3 storage or maybe Google Cloud Storage or your file system to the browser without any middleman, and then showcase, visually inspect all your data. And your data could be like 100 million images on a browser where you can easily navigate through, find the errors, send back to the annotation tool, get back the re-annotations. You can also visually inspect not only the data sets, but also their distributions. Let's say you have annotations like boxes, you want to see what are the bounding box sizes or label distribution categories, how many of them you need. So you can easily have both qualitative and a quantitative grasp of all your data that sits on top of your storage deep lakes. Then, obviously, one of the key things that we have first time have seen this is being able to run queries on top of this data. But not only those are queries that you will expect from SQL, but also what we call it a tensor query language that enables you to do NumPy-like Python computation inside the SQL. What this helps you to do. First of all, you can obviously run a query saying, hey, give me all the images that contain a bicycle during the raining and give it to me. Furthermore, you can do indexing inside the select function. You can say, hey, crop the images 400 pixels and then adjust the bounding boxes to make it correct and give back to me. So what happens behind the scenes, why this is like kind of a different dialect than SQL is one of the key things. Usually, typically in traditional data lakes and like the databases, including formats like Parquet or Pyro, where you see is that each column represents a single dimension. Or if you want to store the images, which are very inefficient, you keep them as like blob storage, but then you can't run any query on top of this. What we enable to do, I think one of the fundamental things that I'll talk on the next slide about the data storage layer, that we help you to store images as a separate column, which we call it a tensor in deep learning frameworks. And then more importantly, here we are enabling you to write custom Python-defined functions. Let's say in this case will be area of intersection, where you want to order by the dataset by the model prediction error, and then create a new dataset with most of your errors so you can feed back to the model and then retrain the model or maybe train a new model. So one of the key things as we see is that this dataset having images, bounding boxes, and then their predictions, you can efficiently build datasets just in the query engine and then get a view. And this view is like a one-liner to connect to the PyTorch to start doing the training processes. Before you start doing the training processes, we introduce this deep learning optimized format for training the data that essentially takes, let's say you have a bunch of images, bunch of labels, converts them into n-dimensional arrays or tensors, and then put it into a columnar storage on top of S3 or any remote storage as well. So you can both efficiently represent the data with all the compression, caching, and everything that's taken over you, so you don't have to worry about this. And materialize the data so you can very efficiently stream this to your deep learning trainings or any computations you have to, or it could be inference, could be a visualization. But one of the key secret sauces for the deep lake, similar to traditional data lakes, they based on Parquet or Avro or C format. You now have a deep learning optimized format that we have been working for the last 2-3 years to make it useful. for your applications. And then you can see here is that both the images, the labels, bounding boxes, they are chunked into chunked arrays laid out on top of object storage. Like images, they are heavy, so you have much bigger chunks. Labels are very lightweight, so you have all the labels into a single chunk. And they are stored as a columnar storage that you can access for your queries, inference, training process, or other use cases you want just to visually inspect them. And then the next thing, once the data is in our format, we actually provide the fastest ever data loader that streams the data from remote storage, or it could be local storage as well, to your GPU training job. And the GPU training job could be a distributed training job. So you can think of this as a Netflix for datasets, where your dataset is stored on a centralized storage like S3, and then very efficiently streamed to the deep learning to be able to run the training process or the inference. We have spent a huge amount of time with our great engineers to be able to optimize every juice out of the network connectivity and the format to be able to accelerate deep learning training process. In some cases, we can see here on AWS, let's say, we can save up to 3 hours of GPU compute cost just because of the startup time. And this is now already a small model trained on an ImageNet. So achieving the same performance as if the data was local machine. So you get to the compute bottleneck computation again. Furthermore, we did another comparison with the rest of the ecosystem across all the data loaders that have been available. And we show that for, let's say, computer vision use cases, our data loader gets the most performant. And there is also a fellow group at Yale Network Systems led by Ophides et al. You can see their white paper that got published on Archive that gives you a full observability on the whole data loader ecosystem and MLOps and how this enables for training purposes. And we are super excited to get this state-of-the-art results into your hands so that you can get started and then use the technology to be able to speed up your training processes. So to be able to recap, you have going from the version control, being able to visualize the data, being able to run queries, create materialized views, and then very efficiently stream this to the training process. And that's what Deep Lake is taking care of you for the rest of the MLOps ecosystem. So you don't have to worry and spend a lot of time on building all this data infrastructure for your organization. Let me just take a step back here. What we have seen over the last 4 years and 5, PyTorch, TensorFlow, now also JAX, they did an amazing job in optimizing the compute on accelerated hardware. And now the bottleneck moved from the compute itself to the network and bringing this data to the deep learning frameworks or accelerated hardware. In Activeloop, using our open source deep lake technology, we have been focused on solving this problem, is handing over the data to the compute. So the bottleneck is no longer the data anymore, is that your computations can run very, very efficiently. And let me show not only the integration to the deep learning frameworks, but also bringing together the modern data stack that has been evolved pretty significantly and separately from the MLOps ecosystem, and then having a conjunction point where you can use all your data that may be stored in a traditional databases, maybe in your data lakes, maybe in your lakehouse, connect through the deep lake to the rest of the MLOps systems with partnership integrations with, let's say, weights and biases, AIMStack, with Anyscale, and all the technologies, including some of our annotation tools, and very efficiently transfer your existing data that's already there, that's in your current stack, into the new trend of the MLOps and data-centric development of your models with leveraging deep learning. In our most belief that deep learning is going to take over the analytical workloads in next 2-3 years and become the de facto standard for all machine learning processing and be like the software 2.0, as Andrei Karpathy mentioned, for running this processing. And Deep Lake is going to be the data foundation for all these operations for your workloads. Let me, instead of too much theory, let us focus on a specific use case that we have prepared for you in collaboration with Intel, showcasing the capabilities there. And as you already have seen, and if you haven't, maybe you should check out the session talking about the Lion dataset. We are going to showcase today a training of a 1 billion parameter clip model using one of the largest public multi-modal datasets with 400 million image text pairs. Let me just revise back. What's happening today is that when you want to start your training process, you have a data somewhere located on S3. You have to go and manually copy to your local laptop or copy to your notebook. Maybe you're doing a distributed training on a cluster. You have to copy each of those nodes and then or run an inference. Every time you modify the dataset itself, you have to go and synchronize the data across the time. And this takes a lot of time, as we will see, for your workflows. And let's say you have a new data scientist trying to solve this problem, then they have to build their own pipeline because they can't reuse your pipeline. They have the different needs, they're different, so there's a lot of complications that's happening even before you start a training process. It used to be the days where for me to start training a very simple model on ImageNet, it took me literally a week to get access to the ImageNet dataset to be able to train this model. And today, the ImageNet considered to be like a 1 million image text pairs. You have 400x or even further larger petabyte scale datasets. That's very difficult to handle all this processing for you. And what we provide, or this is the new way of doing things, is deep lake way of doing things, is being able to stream the data from a centralized storage to all these applications, given there's a high bandwidth connection between the nodes. And you can think of this as a kind of a Netflix for datasets example where your data gets streamed to your nodes as fast as whenever you need them. And then we're going to show what we did got very exciting results. So what we did is that we took one of the largest multimodal open datasets, Lion, 400 million images. We have been able to download only 300 million pairs because the raw pointers they have in the Parquet file had a bunch of errors, validities, because they are open source open on the network internet, and because there are some trivial issues. So the time even taking the 200 million images took us 100 hours to download. Furthermore, once the data has been downloaded, we took that and put it into a deep lake, which just take us 6 hours on a single machine. And then the dataset itself has been 2 terabytes of scale. So this dataset is now have been able to get efficiently read into the deep learning frameworks. Before that, let me actually give this to Eva to be able to run you a demo for you, and so that you can see the dataset, how this has been processed done, and then we can take over and showcase how this will be streamed to the training process.
We're going to start off by introducing Deep Lake's open source component, formerly known as Activeloop Hub. Deep Lake is its latest version that has been super optimized and rewritten in C++, and actually sped up the data streaming by 2 times as compared to the previous Deep Lake versions, as well as when compared to other PyTorch data loaders out there, as verified by an independent study of Yale researchers. So Deep Lake open source helps you build, manage, version control, filter, and visualize data sets for AI. We're focusing on image, video, and audio data. And more importantly, we're letting you to stream your data real time while training ML models in PyTorch or TensorFlow. So let's go ahead and look how this works. So what we're going to do now is see how this works in action. I'm going to pip install Deep Lake and then solve a problem with data access and fast loading. So with Deep Lake, I'm able to load datasets either from local file path or an S3 or Google Drive or even Activeloop Cloud. We have a bunch of pre-upload datasets there in Deep Lake format. I'm going to go ahead and just load MNIST, one of the most popular datasets out there. So there we go. MNIST loaded in under 1 second. Let's see. You can say MNIST is pretty small. How does this fare against larger datasets? So I'm going to try to load Leon. Leon is one of the largest datasets out there, as David has mentioned, and we're going to load it, and it worked in under 2 seconds there. The way we're able to achieve this in this case is we also, not only do we stream the data, but we also store the URLs to the specific images, and we're able to materialize the dataset on the fly. And thanks to the Deep Lake format that's resembling a multi-dimensional NumPy-like array, I'm also able to interface with the dataset to kind of manipulate it as if it was an array. So I'm just going to go ahead here and retrieve the first image. Once we loaded the dataset, we can visualize it. So basically, let's say I've loaded Coco. I'm able to go ahead and visualize it with all its metadata. And metadata is just another tensor or another column in the dataset. So it's all stored in one place. Not only image datasets, but also video datasets. Let's see here. This is a person running in low light conditions. And also, let's say, audio datasets. So here we go. We have some smooth jazz here. Finally, what we want to be doing, obviously, is resolving the data to compute handoff bottleneck. And here, I'm going to show you how Deep Lake interfaces with frameworks like PyTorch and TensorFlow. In this case, let's try to load the Sapphire dataset and then write a simple transform function and the data loader. So the data loader is going to be ds.pytorch. And then just what we're going to do is we're just going to iterate through the data loader. Finally, for the purpose of this Python demo, what we're going to do is we're going to look at dataset version control, and a very important feature for data-centric AI workflows. And Deep Lake offers you to manage your datasets and manage changes to your datasets and save them as your dataset evolves, just like in Git. So basically, you're able to use your favorite functions such as commit, log, branch, checkout, diff, and Evo is actually going to take over and show how to kind of combine all the features of Deep Lake together for data-centric workflows and how these features actually shine the most through the UI.
Here we are visualizing the Cocoa dataset that we just uploaded. Now, if we click on the version control bill here, we see that this dataset has 3 commits. And currently we're on the very first commit, which is the one right after the dataset was uploaded. Now let's run our query where we down select the data based on the classes that are of interest. And so the query has already executed. Now if we check out the very first sample in this query result, we see that we have a stop sign here that is labeled as a stop sign, and it probably is in fact a stop sign, but since the face of the sign is not present, it's unlikely that a computer vision model will identify it correctly, and so we chose to remove this label from the sample. And another edit that we choose to make is that this sample right here is just a very low quality image. It's black and white, it has a very low resolution, and then all of these objects that are labeled with these traffic lights in this car here, there's actually very low certainty about these labels. Like this may or may not be a car, and then same thing with these 2 traffic lights and this one in the distant background. And so we chose to delete this sample as well. And with every modification that we made, we created another commit on the dataset. And so if we cancel this query, let's actually go to one of the new commits. So this latest one will contain both of the edits that we just talked about. So now if we run our query again, we're running the exact same query, except now on a version of the dataset after our edits. We see that this very first sample, the stop sign is no longer labeled. And then index 61 is no longer present. So the sample we deleted would have been in between these 2 images, and it's no longer here. And so subsequent work in our training will take place on this particular version of the dataset, which is essentially the latest commit. Activeloop offers a variety of immensely powerful tools for slicing and dicing your data and then training models on those results. So here we're looking at the Cocoa dataset, which is a very popular computer vision dataset, and let's run a query on it. So we click on Run Query here. This takes SQL style syntax, so I'm going to paste this query where we select images that contains cars, buses, and trucks, and we limit the results to 1,000 of each. And with Shift Enter, I can execute the query, and here are the results. We see lots of images of motor vehicles. Now, most importantly, I can save the query result. And then once the result is saved, I can see it in the query history. There it is right there. And I can then copy this ID and actually use the ID to load the query result in Python in order to train a model. So let's do that next. Now we're in Python, and we load the dataset using hub.load, and then we load the view by running ds.loadView and passing in the ID from the UI. Now we have a dataset view that's ready for training, and we can pass that to .pytorch to get a PyTorch data loader, and then we simply pass that data loader into a training script. And please check out our docs for tons of examples for training different models. Here we are visualizing the Vizdrone training dataset in the Activeloop UI, and we see this dataset has about 6,500 samples. Now, unfortunately, a lot of the samples look like the one here, where the annotations of the objects are extremely tiny. So these cars are really far in the distance, and this is something that's not very relevant for our application, and it's also extremely hard for object detection models to be trained on this type of data. And so let's filter it out. So what we can do is in this query engine, we can use our SQL style query language combined with this NumPy style logic to filter out all the images that contain any objects of label car that have either the width or the height less than 20. Now we could get more elaborate here on the query that we run, but most images contain cars, and so simply filtering based on cars alone and their size is a good proxy for distance from the camera. And so let's run that query. So we see that there are still certain cases where the cars are fairly small, but the problem is not nearly as pronounced as it was before. In general, the smallest objects, or rather the samples containing the really small objects at a far distance, have been eliminated. And we see that now we have about 3,000 samples that met the query condition, so about half of the data has been eliminated. And now when we run this query, we can click on Save Query Result. And then if we look at the query history, we can copy and paste this query ID, and then we'll load that in Python API and then train a model based only on the data that met this query condition. And then we repeat the exact same process for our validation dataset in terms of filtering out the small samples. Now let's look at the testing dataset that we use to evaluate the quality of the model predictions. So again, first we switch to the training run branch, and then let's go to full screen to have a better view of the data. As you can see here, there's a lot of bounding boxes here, and so it's a little tricky to differentiate which ones are the predictions and which ones are the labels. And so to do that, we go to the visualization settings, we go to the model evaluation group, open up the bounding boxes, and then we select the bounding box style to be dotted. And so now the solid lines are our ground truth, and the dotted bounding boxes are the model predictions. And if we sort the predictions based on IOU, let's go to first the highest IOU predictions. We see that in some cases, the model is actually making the right prediction. So it got this 5 pretty correctly. It got this 3 also quite accurately. Like when there's these very clear single digit annotations, the model does a pretty good job of making the right predictions. Now let's actually sort it in the reverse order when the lowest IOU is first. So here now we see quite a few examples of where the model struggled. So let's go through these in more detail. So this one appears to be both potentially mislabeled, and also these numbers are not very clear even for a human, and they're also very small. For this one, the data is flat out misannotated. So the 1 is labeled as a 5, the 5 is labeled as a 6. So actually the model here was more correct than the annotation. So this would be something that we might want to delete from the validation data set. And so again, this is really useful because you can use the tool to go over your data and try to understand what are the areas where your model succeeds and when does it fail, in order to either fix the images where the model might be failing, or potentially to add more representative values where the model is struggling in order to make it predict more accurately under those circumstances.
So let's get back. As you have seen the demo of the data set being visualized, now we'll get into details. What was the process behind the scenes, and what were the results that we have seen during the training process. Essentially, we help the showcase like how you can go like access the data set that takes 100 hours, just pointing to a location here with our open source Python package to be able to grasp the data set. The data set is not downloaded, it just gives you the metadata. And then you can access any random slice or connect to PyTorch and then stream the data while you are running the computation. We fetch the data behind the scenes and take care of all the caching, the compression, feeding into the tensor PyTorch, like let's say format, and then giving it to the GPUs to do the training processing. And we did this in collaboration with Intel's on their CPUs and Ice Lakes. So we're pretty excited about what happened, the results. Furthermore, as I said, to make this even more interesting and complicated, and that we don't recommend to do that at home, is that what we did is that we actually put the data set on US East near the New York on AWS S3 storage, and put a machine on Google Cloud in US Central. So what will happen is that we will go and showcase you how the data gets streamed from one cloud to another cloud, from one state to another state, over half of the US time zone at very high speed. We don't recommend this doing at home because the egress fees are very expensive. And we only did this to demonstrate that the streaming capabilities are good, performant enough to be able to do even remote streaming, even though we recommend all our customers when they deploy the technology to do that inside the data center. So the networking cost is free, or it's not that expensive and can be subsidized by the model compute time. Furthermore, what we did intentionally on Google Cloud, we took a single virtual machine, and the single virtual machine had 16800 GPUs on the same box. why we did that. We wanted to showcase that vertically, this is as optimized as possible. And then you have the ability to horizontally scale the machine cluster, that will like obviously take a horizontal scaling effectively as long as you have the enough network bandwidth from one data center to another data center. And what we achieved is 5 images per second per node shipped to the 16800 GPUs with a training time of much faster, as if the data was local to the machine, but you are now streaming from across a different part of the United States with 75 to 80% of GPU utilization while you're doing distributed training. And most of the bottlenecks you see is actually not because of data fetching, but because of the distributed data model synchronization across the GPUs. And then what if, let's say, you wanted to construct a data set on this GPU machine, or you wanted to copy file by file to the machine? You will just additionally per node spend $4,000 just waiting until the data started. And with Deep Lake, you can only point to a data set with your Python without modifying too much, just the data loader, and then start access the data instantly. So your training time doesn't go down, and then your GPUs are fully utilized, and you can iterate rapidly for your experiments and make your models much better. At Activeloop, we are focused on providing you a solid data foundation for AI. We help you to, in a very simple API for create, store, and collaborate on AI datasets of any size. As we've shown, transform the data and stream very efficiently while training models at scale, query, version control, and explore and visualize, inspect the datasets at scale for AI. And then most importantly, why we all do this is that we can free machine learning and deep learning engineering teams to develop AI products much faster. We have seen the whole exponential growth that happened over the last 10 years, and we expect the same growth to keep up in the next 10 years. And then Deep Lake is going to be a fundamental piece for maintaining all this data infrastructure so you can only worry about the models and focus them. We have seen already deployed this in public companies, and those are the benefits that we have seen, aside from just as we've shown you, like slashing the GPU compute costs, helping the companies to drive more revenue by shipping AI products much faster, increasing data scientists' focus on core business problems rather than actually building an infrastructure themselves, eliminate ML project failure. And we have seen how other companies, like including companies like Tesla, Salesforce, Cruise, they have spent, and they have a team of very great 8 solid data engineers building the same infrastructure and iterating over and over again over the last 3 years. And then once the company realized, okay, their focus is actually not the data infrastructure, but the models, then they have to like maintain the software, which becomes prohibitive costs. And that's where Activeloop Deep Lake comes into the place, helps to take care of all the infrastructure there and let you to focus on your core business problems. Not only that, we have seen a huge growth on the open source community side. We have just reached 1,000 community members, about 5,000 stars. It has been number 2 trending on across all GitHub repositories a year ago, number 1 in Python languages, top 10 in Python ML packages in 2021. And we already have seen dozens of public companies putting this into production, using it now. And we would love you to join the Deep Lake movement. If you want to deep dive into Deep Lake AI, just go to the website. We have published the white papers there. If you have any questions, you want to explore any collaboration, you want to join us with helping the contributing to the system, or you want us to deploy into your organization, just don't feel free to reach out to me personally, David@activeloop.ai. If you have any questions, I'm more than happy to take over and answer any of those. Well, this has been a quite intense information dance sharing with you. At Activeloop, we have been working on this over the last 4 years. We are super excited because this is one of our biggest, largest launches we have ever done of a product that's, we believe, going to has a huge impact on the whole machine learning ops ecosystem, including the specialized in deep learning applications, obviously, and enable companies to do better data-centric development, including connecting to identifying the label errors, doing this inspection visualization of the data, and then very, very efficiently streaming this to the training process. So a data scientist like you will never, ever get bothered about how the data is managed, and that will be efficiently taken care of them. And they can focus on most important thing is to push out these foundational models and have very positive green impact on whole industries with deep learning. So thank you very much for your time, and looking forward to see how the deep lake will be rolled over into your organization. Thanks a lot.